I call this exotic bonds too. I don't love the title. I'm not sure I'm using the word exotic correctly here because these are seemingly everywhere, as you'll soon see. Further, one can argue as to whether bond is the right word rather than more ambiguous interaction. Some of the best things in life are misnomers like starfish, they aren't fish. Jellyfish, also not fish. Seahorses, which aren't horses. Ladybugs, which are beetles. Coconuts, which aren't nuts. Arabic numerals, which are from India, and the list goes on. So if calling negative hyperconjugation an exotic bond is a misnomer, at least it's in good company. So what is this exotic bond that is everywhere, including in every cell in your body? Before I define negative hyperconjugation, perhaps it's worth defining just hyperconjugation. Hyperconjugation, also called positive hyperconjugation, is donation from a filled bonding orbital into an antibonding orbital. An example of where this might occur is in carbocations, where this is the stabilizing effect, making tertiary carbocations more stable than secondary and more stable than primary. We can illustrate with just ethyl cation. In ethyl cation, there is a carbon with an empty p orbital. Positive hyperconjugation is where the electrons of one of the bonding CH orbitals donates into the non-bonding empty orbital. This is the molecular orbital picture. The hybridization theory description might use two different resonance forms like this, where you get some CC double bond character and a proton in the new resonance form. So positive hyperconjugation is an interaction where a bonding orbital donates into an empty non-bonding orbital. Negative hyperconjugation, often found in main group compounds that are hypervalent, is donation from a filled non-bonding orbital into an empty antibonding orbital. A simple example of a compound with negative hyperconjugation is phosphine oxide, OPH3, which is often drawn this way. The problem with this drawing is that it exceeds 8 electrons around the phosphorus atom. There aren't enough valence orbitals for 5 bonds and 10 electrons on a main group atom. So this isn't a real resonance form. In other words, the lines here are not all 2 center 2 electron bonds and something else is happening. The first thing to realize is that phosphine oxide has a major contributor that is an ylide. An ylide is simply a molecule with an adjacent positive and negative charge. The word ylide is what's called a portmanteau, a blended word. We use portmanteaus as a way of creating new words all the time, like brunch, breakfast plus lunch, motel, motor plus hotel, blog, web plus log, email, electronic plus email, internet, interconnected plus network, spam, spice plus ham, Pokemon, pocket plus monsters, Botox, botulinum, and toxin. In this case, ylide comes from the endings YL and IDE. The YL ending is often used for a covalent group like methyl, and IDE ending is often used for ionic components like chloride. So the word ylide implies a blending of covalent and ionic forms. It was originally used because it was thought that something like a phosphine oxide could use resonance forms like this. So ionic and covalent forms. But the form on the right isn't a resonance form. It can't be. However, there is some PO double bond character, and it comes from negative hyperconjugation. Here's our ylide form again, which turns out to be the major resonance contributor. Negative hyperconjugation is donation from a filled non-bonding orbital, the oxygen lone pairs in this case, into an antibonding orbital, the pH sigma star orbitals here. That is the MO description. The hybridization theory description looks like this, where the ylide form is in resonance with forms having a PO double bond and one of the antibonding orbitals for the hydrogens is filled, breaking the bond. This picture, usually drawn for phosphine oxides, is a good composite structure describing all of the resonance forms, but all of the lines are not normal 2 center 2 electron bonds. Using natural resonance theory, we can calculate how much each of the resonance forms above contributes, and these are the results, with the ylide form making up 79% of the ground state, and the other forms, due to negative hyperconjugation, making up about 18%. There are some small contributors not shown. As you might guess from the resonance forms, if we replace the hydrogen in OPH3 with more electronegative things, we can stabilize the negative charge, which leads to more negative hyperconjugation. This is all good in theory, but do we actually have data that suggests this happens in real compounds? The answer is yes, absolutely. Let's look at the experimental structures of triethylphosphine oxide and compare with the perfluorinated derivative. Both compounds have PO and PC bonds. We would expect that the more electronegative fluorinated compound would have more negative hyperconjugation, which would lead to 1. Longer PC bonds, and 2. A shorter PO bond with more double bond character. Here are the parameters of the structures side by side. Exactly the expected structural effects are found consistent with negative hyperconjugation. Here's another example. Let's look at the series OPF3, OPCl3, OPBr3, OPI3, and OPH3. As X becomes more electronegative, the hyperconjugation increases because the anionic charge on X is better supported. As a result, the OP bond should get shorter with more electronegative X and longer with less electronegative X. Again, this is precisely what's found. Where else do you see negative hyperconjugation? Seemingly all over the place. Anytime you have a main group compound that looks hypervalent because of pi bonds, you should look for negative hyperconjugation. Consider the common anion carbonate. Carbonate anion is found in limestone, marble, chalk, and shells of marine organisms like clams and oysters, eggshell, and the baking soda in your kitchen cabinet. It has a major resonance form that looks like this, or really 3 equivalent forms like this, where the percentages below are from natural resonance theory and show how much of that form contributes to the ground state. But there are also forms where a lone pair on one of the anionic oxygens kicks out the other single bond oxygen through negative hyperconjugation to give these resonance forms. Then there's phosphate, PO4 3-, which is found in your bones, teeth, DNA, RNA, and ATP. The main contributor is this ylide form where all of the oxygens have an anionic charge and the phosphorus is a positive charge. Then there's resonance stabilization through negative hyperconjugation. As one last example, consider sulfates, SO4 2- compounds. Sulfates are found in common minerals like the gypsum used in your drywall, but also fertilizers, detergents, cosmetics, and soaps. The main resonance contributor is again the ylide. Then there are numerous forms through negative hyperconjugation. That's negative hyperconjugation, an interaction that explains important aspects of hypervalent compounds with apparent pi bonds. It's exotic in the sense that it isn't your run-of-the-mill 2-center 2-electron bond, but these interactions are found all over the place, including in you. Thanks for watching. We make these videos for fun and to give back to the community. Please subscribe, give us a thumbs up, and take a look at the rest of our playlist, which has a variety of videos at a variety of levels. Hit notifications so you don't miss anything, because we drop vids only occasionally. Thanks.